It's late, I'm tired, so it must be time for Piwars! We are Team Hitchin Hackspace. If you've not heard from us before, we are the people behind Big Hack, which is a enlarged version of the 1980s children's toy Big Track. We made it for really big kids. It's huge. We're also known for renovating an old disused toilet block to make into our new hack space, so we can make all of our cool stuff there now. We're also known for Piwars. We've been 3 years on the trot now. We've done amazingly well. We've never won. We really, really want the win. So in the first year, we were very well known because we came along with a 90-mile-an-hour ball flinger for the Skittles challenge. So contra-rotating wheels, spins it up, very scary. Year 2, we came along with ducted fans. Okay. Unfortunately, we never got it running in time. What happened was, on the day, we had tremendous hardware failure. Basically, all of our autonomous challenges, we failed. And in year 3, we came along with Tito 3. Well, this was our latest incarnation. This is an articulated robot. It gives excellent traction. It is extremely good for obstacles. It will climb a curb, no problems. This thing is very robust. It's of a similar design to the last 2 years in the fact that we have 4 wheels. They don't turn apart from they just rotate. It's skid steering. Each of the 4 wheels is powered, but basically the power is divided to the left and to the right. So on the back here we have 2 motor controllers. So what we have is one for the left and one for the right. We have a Pi. This year we have a purpose-built design breakout board that we got manufactured, and that allowed us to put designated headers and pins for the motors, for the sensors, for the screen. Oh yeah, we have a little OLED I2C screen here. This allows us to see what mode this thing is in at any one time. We also have a little flip-up tray to insert the battery. We were using time of flight sensors. We also used sort of crumple zones on the design. So this is designed to clip into the front here, so it's removable. But it also means if you hit it hard, it bends, and if you hit it really hard, those pins snap. The key decision here was that we could reprint loads of these little pins. They're just bolted on the side here, so we can just unscrew it, take that off, put the new one on. Job's a good one, we can carry on. Skittles. Again, hardware failure. We whilst testing for the event, our Nerf gun that we'd made an attachment for, we actually made a 3D printed magazine holder, and it held 2 contra-rotating wheels which would force the darts through. Had it testing, like here, you can see that it's actually testing. That worked fine and was working brilliantly for like 2 or 3 months before the event. On the day, unfortunately, we were running with cheap servos, and there's a little servo that pulled back an arm and then pushed forwards and pushed the dart into the wheels, and then that gripped it through. As the servo tried to push forward, something happened. The little plastic motors, the little plastic gears inside jammed, and it basically drew way too much current for the underrated 5-volt regulator for the servo, and just popped the electronics, and the Nerf flinger was gone. Obstacle course. We did really well in the obstacle course. Very, very nearly won. The only reason why we didn't win is because when I started in the obstacle course, I'd started too quick. So on our controller, we have, in fact, yeah, on our controller, it's just a PS4 controller. We're using the buttons on top to increase and decrease speed. Now this means that you can either go for full speed, but it's a little bit sort of sketchy, it'll just overshoot things, or you can drop the percentage down and sort of have a bit more controllability. Now I started too quick, so as I went off the line I realised my mistake, and then I stopped and I spent a couple of seconds just dropping the speed down and then carried on slowly. Unfortunately, it was those couple of seconds on dropping the speed down that made us lose the event. I mean, we were like half a second off the lead time, so we would have actually beaten them by 2 or 3 seconds if we hadn't done that. Over the rainbow. The Over the Rainbow course, we did really, really well. We actually won that challenge. Martin, who was the guy in charge of that particular module and the code, he excelled. We'd seen a few sort of methods of how to do this. The complicated one was where the robot starts in the middle and then it rotates to find all the coloured balls, and then it remembers where they are and then drives off. We decided not to go down that route because it's quite complicated and it's prone to a few errors if you don't have everything dialed in exactly right. So what we did was we started in the centre and we then just rotated until we found the first ball that we needed, drove towards it, reversed, rotated again in the same direction until we found the next one. In the end, that actually worked quite well. We got lucky on a couple of them because as it was reversing, it started to turn just as it was reversing. And it ended up doing a J-turn and actually pointed exactly at the ball that we needed to go to next, so we saved quite a lot of time there. But again, that was down to pure luck. So yeah, Over the Rainbow we won. Somewhat lucky, but we'll hone that in so it won't be luck this year. Minimal maze. Again, we did quite well in the minimal maze. We could have gone quicker. It's down to having the smoothness of following the wall and flicking directions and things like that. We did quite well, but we didn't win that one. And of course, when it came to Pi Noon, we won! So we won the 2018 Pi Noon. Very proud of this, very, very happy. And we have one of these for the Over the Rainbow Challenge as well. I look after this one because I was the one driving. Improvements for next year. How do we make ourselves better? Okay, so almost directly, like a week or two after the event, we started working again. We actually made another robot. So we have 2 of these things now. This one is a slightly longer version of the old one. As you can see, it's slightly bigger. It's the same width, everything else is the same. So what did we do that for? Well, the previous robot with the positions on the wheels was actually shorter than it was wide. So it was actually a little bit skittish when it was driving fast in a straight line. And that is great for maneuverability, but it does mean that you can't sort of gun it in a straight line or gun it near in a straight line like on the straight line speed test. So I wanted to improve that one. So made the wheelbase a little bit longer, which actually then gave us a little bit of room inside. So this one, which is actually a fully drivable version, which we're calling Stretch at the moment, actually has a Pi Zero inside the lattice, inside the shell. So that in itself has actually meant that this thing is drivable both ways up. It's flippable, which means when it comes to the obstacle courses and stuff like that, if we accidentally hit something and climb, because this thing will climb, then we can still carry on going. We don't need to rescue it, we just keep going. I'm intending on putting in a tilt switch in there so it knows which way up it is, and if it knows which way up it is, then we can invert the direction axis on the controller automatically, so it'll just carry on going. We don't have to worry about it. The next thing I want to do is I want to make this thing drift. I know it's nothing to do with any of the challenges, but I've had fun with that one driving around in the dirt. I want to do a controllable drift. Now that's extremely hard with 4-wheel skid steering. I've got a clip of Hitch doing donuts and other things in standard 4-wheel mode. So what I'm intending on doing this year is, rather than just having 2 motor controllers divided to the left and right, we're going to have 4. So we're going to have 4 motor controllers, 1 per wheel. So what that will let us do, for my silly idea of having it drift, is that we can control individual wheels. So that will mean that what I can do is have all 4 wheels running at the same speed and then just say drop the speed, so sort of drop the speed on the front left, have it try and brake, and then I can floor it on just the rear 2 and maybe have the front 2 just coast. So try and get it to sort of step out and sort of drift. So I'm not sure if it's possible, but that is something that I want to do. The other thing that the 4-wheel motor controllers will do is if we get stuck like we did in the very first year where we had an object get wedged, a static object got wedged in between the wheels, we couldn't climb it because it was trying to climb, the other one was trying to push it back down again. So what we can do this time is actually have the 2 wheels go in the opposite direction. They could fight each other, but that might mean that we could climb out or try and shift the object out of the way. It gives us just a little bit more control. Now that in itself sounds cool, but when you have a limited control set like this, where you basically have forward, back, left, right, how do you control all 4 wheels in any meaningful manner? I've got a couple of ideas. Don't want to say them just yet, but there's some nice ideas of some sort of semi-automated system. We can also potentially flick modes. We'll see. By the way, we use now the PS4 controller. We've been through, over the last 3 years, we've been through the Nintendo Wii and Nunchuck. That's extremely easy to get started, extremely easy. Love it. It's also very reliable and it's keyed. So that means that if you start it up and boot it up, it just works with it. In the following year, we tried, because we wanted the dual analog sticks. Obviously the Wii and its nunchuck only has the 1 analog stick, but we found that there was a Wii Nintendo Classic controller which works instead of the nunchuck. You have a little controller, and that had 2 analog sticks, and that worked as well. Same kind of pairing, so it worked quite nicely. We didn't have any interference issues or anything like that, but the accuracy of the analog sticks was a bit low. So the left-hand stick, I think you had 32 values over which it could go from the left to the right and forward and back. The right-hand stick only had 16. Now, I'm assuming that we weren't doing it right. I'm assuming that we were using it right and that we weren't doing anything wrong. But that was 16 values forward and back. Just didn't give you the sensitivity that you needed for the control of the throttle. It would step and step back. So we decided to drop that one after that year. Year 3, we used the PS4 controller. Now, we jumped to the PS4, not to the PS3, because on Big Hack, which you've seen before, we used the PS3 controller because that's what we had available at the time. It does work well, and once you've got it all paired up, and it's quite well. It works nicely. You've got the same analog sticks as these, and you've got enough buttons to do everything you need. The main problem is pairing. So normally when you're talking about Bluetooth pairing, you have like a phone connecting to a Bluetooth speaker, and you basically just go, okay, on the phone, find the speaker, hit connect. The Bluetooth speaker says, okay, give me the pin. You type a pin number in, or 0000 or whatever it is, and hit pair. Done. The PS3 controller works slightly different. The PS3 controller actually has a 2-way handshake. So not only does the robot have to ask the controller to pair with it, the controller has to pair back with the robot. So you have that 2-way pairing. And out of every single way, it has always felt like a little bit like black magic when you finally got it working. You didn't want to do it again. So I actually got a bit scared because when we were taking the Big Hack to one of the events, someone else was having difficulty. I think one of their PS3 controllers had run out of battery, and they were asking if anyone had a spare controller. I nearly gave them ours, and at the very last second I thought, no, I can't do that, because if I give them theirs, they'll pair it to their robot, and then it's going to be a nightmare for us to try and repair it on the day at an event. I was just like, we can't risk it. This was an event. This was a time when people were trying to have a bit of fun with Tito and with Big Hack. So we just had to leave it. PS4 controller is back to the usual. The robot just asks the controller to pair with it. Done. It's a lot more. It's a lot simpler, and it just works. I'm much happier with it. Yeah, the main thing that I miss from the controller is the ability to change LED status, because it would be nice, because when you with the Wii Nunchuck, when it paired, it would come up with a blue solid link, and you could set the LEDs to do what you wanted to do. So if you're in different modes, you could change the LED position. This one just has a pairing light. I haven't actually successfully tried any sort of LED status notifications or anything like that. So that's where that the little OLED screen comes in. Oh, that's the other thing. This time, the OLED screen is on the back. At the events, we struggled to see the screen because in our genius, we put the screen facing forwards on the top. So the robot's inevitably going to be sat on the start line pointing away from you. So you're there going, okay, which mode is it in? Which mode is it in? And you're there with the controller going, I think that's down. Yeah. We'd realised within 10 minutes of being on the day that, yeah, that's not what we want. We need to change that one. So I'm quite happy that the screen is now on the rear. What else? Well, the last thing that we want to improve is the wiring. So our wiring has always been reasonably neat. We have been judged down on it a couple of times now because it wasn't sort of cable tied in the neat little straight lines and things like that. So I want to go down that route. I want to get this thing looking beautiful. The other thing that I really want to do is get away from jumper wires and pins and stuff like that, because it's the #1 cause of non-repeatable errors. So all it takes is a knock, and one of those pins could just come loose a little bit, or it could just jump off and back on again, or at least just it could rattle on it and effectively break the connection for a fraction of a second. Now, if that's on a motor controller, it might send your motors to do a bit of a weird thing. They might just blip, or they might turn off and reset. Or worse, it's on the power for the Pi, and the whole thing reboots. And if you're mid-challenge, that's the last thing you want to do. So that's where we are. That's where our development is heading. I hope you like it. So yeah, thanks. Bye.